Hey everyone, so my name is Tom Riley and today my talk is basically going to be around how in the last 2 years I've done some work with Prometheus and how I've discovered a pattern for successfully operating it within Kubernetes. So I'm based in Manchester. I currently work on infrastructure at Nuance. I've literally just changed role, but as of before 2 weeks ago, I spent 2 years working at Booking.com in a team building out a Kubernetes-based platform, and I spent most of my time working on the monitoring and observability tooling. So here I am now to speak about some of the things I've learned. So I'm hiding behind my laptop today because I'm actually going to do a couple of demos as I go through this, which is a bit brave, but we'll see how it goes. To begin with, I'm going to give a bit of an introduction around Prometheus, what it actually is, very briefly talk around how you can use it to monitor Kubernetes, and then I'm going to dive into the actual high availability and also a little bit around long-term storage. So, brief introduction to Prometheus. So if you've never used it, it's a time series database and a set of tooling as well. It was developed by SoundCloud in 2012, and they open sourced it. And then a couple of years later, in 2016, it joined the Cloud Native Compute Foundation as a incubated project. And then in 2018, it was actually the second project to graduate from incubation alongside Kubernetes within the CNCF. So what actually is Prometheus? So it's a thing you deploy, it's just a binary that you can run. We're going to look at how it's running in Kubernetes in a minute. But once you've got it there, you then need to configure it with a number of targets that it will then monitor. So if we deploy an application into our environment, we then need to expose a Prometheus formatted endpoint for that application. A Prometheus endpoint is a HTTP endpoint with a load of text. Once you've got that, you can then configure targets in Prometheus, and it will go away and it will start scraping those metrics into the time series database. So this is an actual example of what a Prometheus endpoint would look like that you may expose from your application. On first glance, it just looks like a load of text. If we zoom into one, we can see here there's a metric called JVM threads states threads. With Prometheus, you have a concept of metrics and labels. So within your metric, you can then use labels to actually add some more context around sort of different versions of that metric. And then, of course, you have your actual value of the metric. So you combine those two things, you have your value and you have your metric value. Sorry. So that's how we start scraping data. Prometheus then also has a service discovery component. So out of the box, it has service discovery for lots of different platforms, one of which being Kubernetes. So when we deploy Prometheus into Kubernetes, it's automatically going to be aware of certain things and start collecting some additional information for us automatically, which is really awesome. Next, not every application or bit of infrastructure out there supports Prometheus out of the box. So there is a pattern called Prometheus exporters. So the concept is, let's take an example like Elasticsearch. Elasticsearch doesn't out the box expose a Prometheus endpoint, but somebody has written an exporter that will interrogate Elasticsearch on its own native APIs and then expose a Prometheus endpoint with the metrics from the exporter. So once you've then got metrics into Prometheus, at that point you may actually want to start using that information and have alerts. So you can configure rules within Prometheus. So you might have a rule that says if metric HTTP 500 spikes above 10 for a duration of 3 minutes, fire an alert. Once that alert fires, it goes into an external tool called Alert Manager, and from there you can write rules to send your alerts to Slack, PagerDuty, whichever tool you prefer. Last but not least, once you've got these metrics, you want to make lots of pretty dashboards. So the Prometheus API is pretty widely used in the industry, and obviously Grafana is one of the main dashboarding tools that supports it. So that was my very brief introduction. I have an environment on my laptop that I'm going to use during this talk to do some demonstrations. So I have a Kubernetes cluster running on my laptop using Docker, using something called Kubernetes in Docker. I then have something deployed called the Prometheus operator, which I'm going to go into more in a second. I'm actually using that to automatically deploy Prometheus. I then have 3 components that I'm using to actually monitor Kubernetes. One is kube state metrics. So this is effectively a Prometheus exporter that looks at Kubernetes and exposes information around the actual cluster state. So within Kubernetes, you have things like pods, deployments, stateful sets, all these different resources. This will actually expose metrics about all of those resources inside Kubernetes. We then have the node exporter. So the node exporter is not specific to Kubernetes. It's something that the Prometheus project created. It's effectively for running on your nodes and exposing metrics around hardware and the actual operating system. Lastly, we then have Kubelet and cAdvisor. So these are actually components of Kubernetes that expose Prometheus metrics out of the box. So we can scrape those into Prometheus. And these will tell us information around the actual containers running on the nodes and give us useful metrics around like resource usage of CPU and memory. Last but not least, we've also got Grafana deployed with some dashboards that we're going to use. So I mentioned the Prometheus operator just then, and this is a pretty sort of key component to what we're going to look at today. For anyone that's not aware, an operator in Kubernetes is effectively a method of extending the functionality. So out the box, Kubernetes has a concept of pods. Inside a pod, you can deploy 1 or more containers, and you can use that to deploy your services. If you want to deploy many pods, you might use something like a deployment, and that will go away and deploy X number of pods with your application inside. If you wanted to handle state, if you had something that was storing data that you wanted to persist between restarts of your service, you could use a stateful set. These are all out-the-box features of Kubernetes, and we could totally go away and use those to deploy Prometheus ourselves and build our own sort of orchestration around that. But the Prometheus operator sort of uses those components for us automatically, and instead of having to do a deployment, I can just tell the cluster to deploy me a Prometheus, and it will go away and understand the logic of doing that for me. So what does that look like? So here is a snippet of YAML, and if anyone's familiar with Kubernetes, you get quite familiar with YAML pretty quickly. You don't like YAML, you probably won't like Kubernetes. So in this example, at the top, I've highlighted kind equals Prometheus, so I'm explicitly saying that this resource is type Prometheus, and this is something that the Prometheus operator will watch for and then handle when that is applied to the cluster. Some of the other components I've highlighted, you'll see, are actually specific to Prometheus itself. So there's an example in there of retention of 12 hours. So this is me saying that the Prometheus that gets deployed into Kubernetes should retain its metrics for 12 hours. The operator will see that and automatically apply the configuration for that into Prometheus. I don't have to build any orchestration for that myself, it's just fully automated. So if we fire that into Kubernetes, we'll end up with the Prometheus instance. So the operator doesn't just deploy Prometheus, we can then use it to configure Prometheus as well. So if we have lots of services running inside Kubernetes, and they all have a Prometheus endpoint, we need to actually tell Prometheus about those targets. So this is an example of a service monitor, and the clue's kind of in the name. You define the services you wish to monitor. So 3 useful bits of information that I'm specifying in here. In the middle, the namespace selector. So I'm telling the operator that the namespace it needs to look at, in this case, is Prometheus. And then we have a selector at the bottom using labels. I'm going to say, look for a service with the label app equals Prometheus. The operator can then look in the Prometheus namespace, find the Prometheus service. It can then use that service to identify the containers or pods running in Kubernetes that I wish to monitor. At that point, we then have the endpoint section in the middle, where I'm specifying that the path/metrics on port 9090 is where the metrics can be found, and that it should scrape them every 30 seconds. So with that in mind, let's actually have a look at how that looks. So I'm not going to dwell on this too much, because it's just lots of YAML, but you can see here that I have my Prometheus resource that I just showed in the slides. I've already applied this into a cluster that's been running on my laptop for the last half an hour. So we have two things. We have Prometheus automatically running, one instance. If nobody's seen Prometheus before, this is the standard UI that you get out of the box. If I come into status configuration, we can see there is a hell of a lot of config. I've not had to write any of that because the operator has seen that I have applied 4 service monitors, and it's gone away and used that information to automatically find the pods that I wish to monitor, and then automatically updated the config in Prometheus. I've never actually had to write any custom config for Prometheus. The operator's just always done that for me. So once it's got that config, it can automatically go away and identify its targets. So we can see a number of things in here. We can see that it has identified Prometheus itself, so I'm using Prometheus to monitor itself. We have our node exporters, so the node exporter for collecting information about the actual hardware, the actual nodes, and the OS. It's running as a daemon set in the cluster, so that's running on every single node. And Prometheus is scraping metrics off the node exporter on each node. Likewise, kubelet is also on every node, so we're automatically scraping those metrics. And last but not least, I mentioned kube state metrics. So that is a single pod interrogating Kubernetes and exposing lots of information about the cluster state. So that's one pod that we're scraping. In the middle here, we have these labels that have automatically populated. So any metrics that come from these sources will automatically have things like the namespace, that it's actually inside Kubernetes, or the service that it's exposed behind. This was the service discovery component I mentioned, so I've not had to configure that, just it knows it's running inside Kubernetes and it's done that automatically. So I could come into the graph section and I could run a query, so kube deployment created. This is a metric exposed by kube state metrics. It's come back with 6 time series, and it just so happens that if we look in the cluster, in all namespaces, for the number of, just so happens we also have 6 deployments in the cluster, so you can see where that's come from. Look at this UI though, it's a bit basic and not actually what you would use for monitoring. You would plug that into Grafana. So I've got 2 dashboards here that I want to show you. This is just showing me information about the Kubernetes cluster. So here we can see the load of our 3 nodes in the cluster. We can see the memory usage. We can see idle CPU. We can see disk I/O. We can see memory-intensive pods in the cluster. You sort of get the idea around actually monitoring the cluster. We then have this other dashboard which shows information related to the actual resources inside Kubernetes. So I can say, show me the Prometheus stateful sets, which is what the operators use to deploy Prometheus. I can see the memory being used. I can see the CPU being used by Prometheus. I can scroll down. I can see that it's barely using any CPU. Memory is slowly creeping up as it collects more metrics. But this is actually a really good dashboard where you can see we're using the metrics from kubestate metrics. So we've got the actual information of what's running in the cluster, and then we're tying that to the actual information from kubelet about the amount of memory being used or CPU being used by those pods. So I want to just come back to this dashboard before we proceed. So if we look at our environment, you can see a number of pods running. So we have the actual operator pod. We have a single instance of Prometheus. And then we have the node exporter, kubestate metrics, and Grafana components I've just demonstrated. Now, this is great, but what happens if this pod goes down? The Prometheus pod goes, we lose Prometheus, we stop collecting metrics, and we also stop displaying metrics, which isn't very good. So I kind of coin this as highly unavailable Prometheus. If I go into the cluster now and hit delete, then reload Grafana, yeah, you're going to see no metrics. You're going to have to wait for Prometheus to come back up and start collecting fresh metrics again. Of course, it might not just be me going in there and doing that. It could be a node failure. It could be an actual bug in Prometheus. There's many different reasons why that might happen. So how can we make that highly available? Well, Prometheus itself isn't actually that complicated. You just feed it some configuration. It goes away and finds a target. It starts collecting metrics. So we can actually just run multiple instances of Prometheus, and each instance will go away and perform that scrape operation. Of course, we need to actually decide which instance of Prometheus we then might use. So we could use a load balancer to do that for us. But since we're running in Kubernetes, we could use a Kubernetes service, which is the native sort of internal load balancing feature of Kubernetes. So I'm now going to just make a change to our deployment that on our Prometheus resource, I'm going to set replicas to 2, so the operator will see this and then automatically go and deploy a second instance of Prometheus for us. So I've just applied that via a script, and we can now see that we now have another instance of Prometheus, and it's successfully running. So if we jump back into Prometheus, one thing we will see is, because I did configure Prometheus to monitor itself, we're going to automatically see that target come up. So we're now scraping metrics from 2 Prometheus instances, and each of them are scraping all of the other metrics we want as well. So if we jump into Grafana, things should be great, right? If I start refreshing, yep, that looks good. That dashboard there is missing some data, and you're going to sort of see where I'm going with this now, that yes, we've got 2 instances, but one's got half an hour of metrics, the other's got the last minute. So that's a bit of an issue for us. So let's talk about that. So yes, there's a few reasons why that's an issue. So one of our instances has half an hour of metrics, the other has a minute. So if we're just load balancing the requests for queries across those 2, we're going to see those differences. Also, there's no coordination between the different instances of Prometheus that we run. So although they're scraping the same target to the same configuration, there's no guarantee they'll do it at the same time. So if they each hit the Prometheus endpoints at slightly different times, the metrics may differ. So even if these 2 instances we had been running for the same amount of time, when we do the refresh, we'll see the graphs just change ever so slightly, which is a pretty poor user experience. So one way around this is we could use some sort of sticky load balancing solution to ensure we pin queries that come in on the same node each time. But that feels kind of horrible, and also isn't going to scale with load. So we'd end up pinning load on a single instance, and we'd have to then continuously vertically scale that as we need it to be more performant. So when I was working at Booking.com and we were thinking about how we would get around this and actually make this highly available in a nice working way, we discovered the Thanos project. So when we first saw Thanos, they have this tagline on the repo that it's a set of components that can be composed into a highly available metric system with unlimited capacity. It kind of seemed a bit too good to be true, but as I'm hopefully going to demonstrate now, it literally can do that. So it was originally created by some engineers at a company called Improbable down in London, they're a gaming company. In the last few months, they have donated the Thanos project to the CNCF to become a sandbox project, and there's a number of maintainers for Thanos who actually are also Prometheus maintainers, so it seems to be gaining some good traction and is a very busy looking repository. So how does Thanos differ? So this is the environment we have right now on my laptop. We've got 2 instances, each scraping the metrics twice. To use Thanos, we deploy what we call a sidecar. So inside the Kubernetes pod, we deploy Thanos running alongside Prometheus. So the concept of a sidecar in the world of Kubernetes is you have a pod with 1 or more container. I'm adding an additional container to run alongside Prometheus to sort of enhance or add more functionality, so we call it a sidecar. Once we've deployed that sidecar, we then deploy another API called Thanos Query, and Thanos Query will be aware of each sidecar running alongside Prometheus in our Kubernetes cluster. And then Thanos Query exposes a HTTP API, which is literally just the Prometheus API, and we'll take a look at that in a second. So to achieve this, this is still all deployed with the Prometheus operator. So the operator is capable of using Thanos. Inside our Prometheus resource, we're now adding a section called Thanos. And in here, I'm telling it two things. I'm telling it the resources to allow the sidecar to run with, and I'm telling it the version of Thanos to use. Also, I need to deploy the Thanos query layer that I mentioned. There's nothing too fancy about Thanos Query. You can run as many or little of these as you want. They scale horizontally quite nicely, so I'm just running it as a regular deployment inside Kubernetes. In our example, we're just going to run one of these, and it's going to deploy the Thanos container image. So I've wrapped this up in a script as well, so I'm not just running commands for half an hour. But what we're going to see is was pretty much already happened, but the Prometheuses are restarting with the additional sidecar. So you can see now, before it was ready 3 out of 3, now it's ready 4 out of 4. If we take one of these and just do a describe on it, we can see that the operator has redeployed these with the addition of the sidecar there. We also now have the Thanos query pod running, so we can make use of that, and I have also just automatically redeployed to Grafana, so Grafana is now pointing at the Thanos query API instead of at the Prometheus instance directly. So how do things differ? So Prometheus itself, I can still hit that. That looks absolutely no different from that perspective. I could still come in here and query one of the nodes directly if I wanted to. Grafana, now I'm now pleased to say each time I refresh Grafana, the metrics look exactly the same. If I zoom in, you can see each time it looks no different. Even though there's slightly different metrics between the two, it has this deterministic approach of determining one time series. So each time you query, it runs the query against both instances of Prometheus and builds up that time series. So it'll look at one instance of Prometheus. If there's a gap, it'll then flip to the other one, and it'll keep doing that until it builds that same time series each time. So not only is it highly available, it's consistently generating the same time series. So last but not least, we have Thanos query. So this looks exactly like Prometheus. It's actually based on the same code base. I can run queries. So this time when I run kube deployment creative, we're going to get an extra deployment because I've just deployed Thanos query. So we've got 7. I can actually turn off the deduplication and it will return 14. So we'll get the metrics from both. Obviously in production, there's no reason you'd want to do that because we actually want the deduplication to occur because we only want one time series. One interesting section that is added is this store section. So Thanos is reporting that it can see our 2 sidecars. They're both up and they're both running perfectly fine. So that's our highly available Prometheus. Last but not least, once you've got to this point, you've got Thanos there. There's one other massive benefit it can give you for free, if you like. Prometheus was never really designed for long-term storage from day one. So if you want to add more storage, you might have to just bigger and bigger and bigger, which is not great. And instead of long-term storage, it's more like long-term nightmare for someone at some point in the future. The Prometheus project sort of tried to tackle this. They added this remote write API, so you could actually push metrics out to another system like Elasticsearch. At Booking, we wanted to avoid that because Elasticsearch is very complicated and we wanted our metric system to be as simple as possible. So again, here comes Thanos. So this is the environment we have with the sidecars and with query. We now go away and we configure Thanos sidecar to now be aware of a S3 or GCS or whichever bucket technology you wish to use. Once it has this, in its config, it will start pushing data, those metrics, up into that bucket. And we then expose a API in front of that bucket called Thanos Store. Once Thanos Store is there, the query layer will automatically become aware of it via the same discovery process that used to find the sidecars. And we will then run queries in Thanos Query, and we will be querying against our local Prometheuses and the long-term metrics sitting in the GCS bucket in my example. How does this work onto the HUD? So Prometheus is running inside a pod. We configure it to start scraping our targets. It stores metrics inside a block in memory, and then every 2 hours it starts pushing those metrics out to disk. Because Thanos is running inside the same pod as Prometheus, it has the same file system, so it can see those metrics sitting on the file system. So when they are written and complete, it will start pushing them up to the bucket automatically. There's a ton of benefits to doing this, but the big one to shout out is that if you were to just vertically scale, SSDs are very expensive, and eventually you're going to hit a point where you can no longer vertically scale. So storing your metrics inside that bucket over the month or the year long periods is much more cost effective. And unbelievably, like performance-wise, very little difference, which kind of surprised me when I first saw it. So my last very quick demo. So inside our Prometheus resource, I've added an additional config that defines the bucket configuration. So once I apply that, Prometheus is automatically going to get restarted again, which it has done, and it's also deployed the Thanos Store component. So if we jump back into Thanos this time and refresh, it's automatically seeing the store via DNS discovery, and it's going to rotate and see new Prometheus sidecars that have just been restarted. So at this point, if I run a query now, I guess it's not a great demo because I've only been running this environment for half an hour, but if we were running this environment for a couple of hours, metrics would start going up into the bucket, and when we run the query in Thanos, or in a tool like Grafana, which points at Thanos, it's going to query across local Prometheuses and the bucket and automatically deduplicate for us. So in conclusion, I only briefly skimmed over the operator, but the Prometheus operator is actually really brilliant. From experience with Kubernetes, there's some operators that aren't very good, but the Prometheus one's been around for quite a while, and it's pretty mature and well maintained. When you're running Prometheus, literally scrape metrics from everywhere. So I've shown a few samples of metrics already inside Kubernetes or ones we can add in, and then the real clever bit with the high availability in Thanos, if you're running Prometheus in Kubernetes, I strongly advise you go take a look at Thanos, because it made running Prometheus really easy. Love a cheesy slide. I kind of discovered after working with this for a bit that Kubernetes and Prometheus do run together really well. That's me. Thanks for listening. I've got some tutorials up on a website where you could go away and deploy all of this, following some instructions, but feel free to reach out if anyone has any questions at any point. Email, Slack, Twitter. Happy to chat Kubernetes or Prometheus anytime. Thank you.